Uh, Good evening, everyone. Let's start the seminar, and I have the pleasure to introduce the Professor Jorge Aguayo to talk to us about variational and numerical approach to model inverse problems applied in subduction as equates.
So first of all, thank you to all of you to be here to hear me to talk about the first part of my postdoctoral research. This is a work during Dr. Jorge Araneda from CIMA, Universidad de Concepción. This is my postdoctoral advisor. And the idea is to talk about parents. So the idea is could be very simple when I try to explain you, but in the mathematical way and in the process will be very complicated. But the idea is for us in Chile and, for example, United States and Japan, very critical. We have here, in the case of Chile, the South America plate and the Nazca plate. Both plates are in collision constantly, but in the particular case of Chile, we have subduction. So one plate is moving, is diving the other plate. So in that movement, named as subduction, we could have very critical earthquakes. For example, in the 1960 in Bolivia, the biggest earthquake in terms of magnitude were recorded in Chile in 1960. Devastating almost the entire city with very critical problems in the city. But the idea is we have here the tectonic fault, when we can measure some things, in particular the coseismic slip. This is a discontinuity jump in the displacement. We can model this problem as a elasticity equation problem. But the idea is to use this observation region here in this part and in this part to measure the displacement in that part. So we need to recover the displacement jump in that part to recreate the entire airway. So the classical linear elasticity equations, this is no novelty. We have the Lamé coefficients, and we have these boundary conditions. But the idea in the fault is to incorporate three particular discontinuity conditions.
Okay. What is it?
Let me explain you. Okay. So in this part, gamma f represents the fault generated by term. So in this part, we need to impose three things. First of all, we don't have jump in the normal direction. The tractions are preserved also, but we only have jump in the tangent directions. That represents subduction in this part. Another thing is just the same things that we have in the linear elasticity equations. So that's the idea. The idea is to recover that parameters. Yep.
What is tangent there and normal?
The normal is in the outer directions, and the tangent is just the span for the directions. Into this, just that direction or that direction. In 3D, you need to incorporate more vectors.
Okay,
so it depends of the dimension. But it is to span the entire space. So some definitions in a context of a mixed formulation, we need to add more terms. In this case, we need to incorporate this term. This is nada u minus the spherical part, so it will present just the skew symmetrical part. In geophysics, it's called the rotational part. It's very practical in some sense. The jump will be just a span of the tangent part. And we have some very convenient spaces, HD in particular. So we want to propose a variational formulation.
What is HD?
HD is the space of the L2, the L2 vectors with the divergence L2. That is HD. So you have L2 vectors, but the divergence is also in L2.
Sorry,
No worries.
So you are working in a fixed time.
Yeah, yes, just it's not in time, it's just it's stationary.
Okay, but the earthquake already happened.
Yes, the idea is just model the part after the error.
Okay.
Yes, maybe 1 minute, 2 minutes when all the moving is gone. So you analyze the before and after. That's the because we can recover this in online. So the idea is to use interaction by parts to recover a new mixed formulation. We consider this the inner product in L2. This is a very convenient notation. So we can decompose this term as two terms because have this symmetrical part of the gradient. But that part we need to adapt to generate a new variation formulation, but also we need to make appear the term that we need, the jump. So the good term, or the good way to do it is separate this term in a symmetric and a skew-symmetric part, because this term is equal to 0. So in the second part, this term will be decomposed using integration by parts, but this term appears. This term is very important for us. So if we denote this as the tangent part of a vector following a normal direction, we can obtain this composition. This composition. This is the average in a edge, and finally we can obtain this new term that appears in the right-hand side, just combining in the terms of identification of parameters, because we can propose a new way to recover that right-hand side. Right-hand side are very convenient in optimal control problems. And finally, we can obtain the other conditions. For example, the skew-symmetric part must be orthogonal to any symmetric expression. And the problem could be rewritten in a mixed formulation, like the equation number 8. So, in this case, we have this variational formulation, and a beautiful theorem say us that this problem has unique solution in the appropriate solid space. But the most important part is we are changing some things from the traditional formulations. First of all, the Dirichlet condition is just exposed in a weak way. But the normal condition, the traction condition, in gamma n, we need to impose in the space directly, as it were a traditional Dirichlet condition. You are changing the roles. But we need to impose a way to recover the coseismic slip. So we need to impose the set of admissible conditions. We need to impose that the coseismic slip must be in A1/2. A very strange space in substance. And we need to impose some spaces for the control and the states. And A is the map that linear control returns the states, the solution of the mixed formulation. My control in this case will be the coseismic slip. the thing that we need to recover at the discontinuity is the discontinuity gap. The idea is to recover that gap. So in the figure of the whiteboard, markers are not working so well. But the idea, Hane, is we have the plates moving one to each other. So in this part, for example, the movement will be similar to this, but in the other side is doing in the other direction. So you have a discontinuity, yeah, and we need to recover that discontinuity. So that's it. That will be the control in our case. Discontinuity, yeah. And in the linear formulation, our control will be S. That will be the control, the parameter that we need to recover.
You need to recover, or you need to, or is your control?
Well, the idea is yes, S is our control, but we need to recover also the interval.
And then what is the, when you define?
Well, this is the condition to solve the direct problem given a control. We need the result to define the inverse problem in general. We need to have some continuity conditions here, but also for the inverse problem, we also need a very not so stability inequality for the problem. We are looking for a way to obtain the estimation. But right now we have some good advances in terms of the optimal control problem. We are so close to obtain the inequality in the inverse sense, but right now we are only prepared to send you some results in the numerical part and in the optimal control.
Given the jumps, recover
Yes,
displacement.
that's the idea.
Every
In a jump, we recover the entire displacement field. But the problem is trying to just taking some measurements in the surface. We want to recover the discontinuity jump in the entire fall. That's the idea. So we also have a problem. We want to use a reference, the measurements that we obtain from the surface. This could be punctual or a lot of punctual measurements. But the idea is to compare in some sense. What's the problem? In the variational formulation, the displacement are in L2. L2 has no trace. It's a complicated problem. But one way to obtain a trace is maybe doing a projection from L2 to H1. So we are comparing a projection from L2 to P1 for the displacement with a reference in an observation region, and we need to add some penalization term. It's the classic Tikhonov term for the also. Tomorrow it's anyway, subject to the PDE, and obviously the control must be in the required space. So the functional gauge is strongly convex, and the problem in general has a unique solution. It's very simple because the problem is linear, everything works well, but in the numerical sense, could be complicated. Obviously, we need to define a Lagrangian. It's a very big expression. We can obtain the classical unit equation for the problem. And first order and second order optimality conditions are very simple. In this case, the derivative of J must be equal to 0, the first order optimality condition, and the second one, the second derivative of J must be elliptic in some sense. In particular, we have the optimality conditions are this expression must be equal to 0 for every S, and the optimal control is given by this term, and this term is very, very special because we have the raised operator from h minus half to h half, and the second derivative is very practical because the result gives us that we have a classic convex function that we need. Very similar to a calculus on several variables. In sense, it's the same. But we want to discretize this in a finite element sense. So we have a triangulation and we define a lot of finite element spaces. In particular, we need to define the BBM space for the tensor, for the stress tensor. And this space is very special because this space presents information between edges in the normal direction. It's not punctual, it's just in the normal direction. So that's why the finite element is just has divergence, but we don't have continuity in the derivatives. So we can't use this for example, H1 spaces just for HG. And for the H2 spaces are just using discontinuous alerting. So it's constant, for example, or it's a polynomial of degree k in every element, but we don't have continuity. So it's very practical when we need to model some L2 things, especially when we have jumps. And the idea is to define the space for the states. And the most important thing is for the direct problem, we have unique solution. So the discrete spaces verify some good properties, in particular the odd hypothesis for the Babushka-Brezzi theorem. And using interpolation and Sea lemma results, we can obtain a convergence result. And the convergence result depends on the grade of the degree of the spaces. For example, if I use EBN with degree equal to 1 and just a constant discontinuous Galerkin space for the displacement and the rotational, we cannot take convergence with k equal to 1. Sorry, with k equal to 0. So we recover the order h when h is the larger edge in the mesh. But the problem is, for the direct problem, we have a result of convergence. And we obtain something similar for the optimal control problem. This is not usual in the finite element and in the numerical community, talking about optimal control problems. There is not a lot of papers about it. It would be very complicated to find some literature or an answer for this direct problem. We don't have a lot of information. So the idea is to generate, obviously, another interpolation, in this case, the projection from the L2 to H1, but which H1 we need. In this case, just the classical continuous Lagrangian polynomials. In that finite element space, we're doing the projection. So we need to do a lot of things in the numerical part to obtain our or control, and also the electron of the control. We need to recover something in H1/2. It's a very complicated space in some sense, but H1/2 have a representant in H1. And the classical space for H1 are just PK, continuous polynomial Lagrange elements with degree equal to K, with K an integer greater or equal to 1. So the idea is to choose properly the degrees of every space to take points. It's not the idea to be so deeper into finite element theory. So we have some technical lemmas. This is just some classical lemmas in the sense of JH, the discretization of J, have some properties, in particular 1 and 2 are very classical. The second one is just an approximation property, and the first one is a Lipschitz property for the first derivative. And the idea is to obtain this kind of results for the finite element approximation. You can see this term. This term is very bad for us. When alpha is going to 0, this term is closed. And this term would ruin the entire theory when alpha is smaller and smaller. Alpha is the penalization term here. This is this parameter. When alpha is going to 0, we are just minimizing this term in the mostly value of the time. When alpha is bigger, whereas you are saying that this term is damping all the effect. So we are just minimizing maybe this term, but not this term. So alpha is just a weight. And the proof is very generic in the numerical sense. We are separating this in 2 terms using the Lagrange interpolator. So the first term is just an interpolation error, but the second one depends just from depends only the discretization. So we're using the second order optimality condition. That's the idea. And the mean value theorem. So we are using some tricks. First of all, we have this property, mean value theorem right now. And we have these 2 terms. This term is equal to 0. This term is just a copy of this one. And this one is also equal to 0. Both this and this are bounded for the previous lemma. That's the trick. And after that is just applying the results, and we obtain the convergence result. The problem is to generate good examples to test the solver and verify the optimality bounds. So we are proposing something very simple. We don't have yet. So we are trying to recover a control equal to 0. Will be very dummy in some sense, but that's true. We need to recover something dummy. We are using Lamé coefficient equal to 1. It's a very simple example, just a polynomial solution. And the control is equal to 0, and gain must be equal to 0. So we need to recover everything in an exactly way. And the observation region is located here. In a zone when a Neumann boundary condition is fixed. And you can see the error curves are very parallel to an order equal to 1 for almost everything except one thing, J. The convergence of J is an order equal to 2. we're expecting order equal to 1, but the order that we recover is 2. It's very surprising for us. We recover the same order for the states and the beyond states. But yet, we recover order equal to 2. Why? We don't know. But the theoretical results depends of some hypotheses about the results of the direct problem in the continuous sense. For example, our solutions are in H2 or bigger spaces. So we have some smoothness good results for the direct problem that we can use in the finite element problem. But would be possible that we don't have the hypothesis, the optimal order will be not reachable in our numerical experiments. That happens in the second example. In the second example, the idea is to not have a real solution, so we test in a very refined mesh, hyper refined, imposes some results. So we have some U reference fixed in gamma in this part in the observation region. And we pose U, G, and F equal to 0. So all the boundary conditions are equal to 0. So we want to recover this jump given this observation. So in a numerical sense, we have this solution. It's very beautiful with a lot of colors. The idea is we have in UX, we have continuity right now, but we have jump in the Y direction. That's what happened in the model. But you can see some weird things. When I was saying, talking about the earthquakes. in the sigma tensor. But we don't see in this point, just in the origin, we have some discontinuity jump. So we can say properly that this solution is in HD space. It has something working not so well. Also in the rotational pair, we have some little discontinuity in the origin. And also the jump that we recover have a lot of oscillations, particularly near the intersection between the fault and the observation rate. So we have some points where the things are not working very well. And the results are not so good as we expected. Well, first of all, the discontinuity jump is following the good convergence error and also the displacement. But the other things, the rotational and also the error for the stresses are not following the complete one order. When the mesh is refined carefully. Okay. Yep.
In the previous slide, which is the start solution?
The solution we don't know. The idea is just using a refined mesh. And that's the solution that we want to expect.
And how do you define the error?
When we find the error, we're comparing with this hyper refined mesh. So we have a coarse mesh, we interpolate for the hyper refined mesh, and we compute the errors. It's a L2 or HD depending on the mesh.
But which is the solution for the hyper refined?
This is the solution for the hyper refined mesh.
Okay.
That's the solution, and we compare all the solutions for the coarse mesh with that.
It's the correct one.
Yeah. So the idea is to recover a good orders, but we don't have good news at respect, particularly for the adjoint states. We only can recover at 8.5 error order. That's not what we want. but not for the entire adjoint states, just for the adjoint of the stress and rotation. For the error given by the, well, sorry, for the adjoint state corresponding to the displacement, the error is equal to 1. It's very particular, but also is given by the measurement, because we are measure the displacement. It's more obvious that we want to impose more convergence in the part. That's our own hypothesis. Maybe we could be doing something bad, but that's what we recover. But right now we have some experience in a realistic case, very similar to the situation here in Chile. But also, before that, that's the recovery of the gondolas. With h equal 1 divided 8, we have that recovery. When we are doing more refinements, the optimal control is more similar to the curve in black or reference. But we can you can see here some little noise, given because we have a lot of oscillation in the part. That's the part that we can't recover just doing uniform refinements. We need to do something new, maybe an adaptive refinement. That's the part that we want to advance into numerical experiments. But right now we have something new, a realistic practice. In this case, we want to take observations into two sides of the fault. And we want to recover the coseismic slip in this case. So this is very similar to the Chilean case, a South American plate and an Nazca plate. And we want to recover a jump in fact we can impose here. We impose a jump given by a Gaussian function. And the idea is to have a beautiful recovery. So in the left, given a jump, we obtain this solution for the x and y component of the displacement. We solve the optimal control problem, and we obtain the optimal states. Can you see a difference? It's almost equal, with some details, very little details here and here. But you can see the difference, for example, right now. But the recovery is almost perfect, except here. You can see a little difference here. Explanation will be made it in method. We are discussing about the mixed formulation because that's a lot of issues when we are trying to solve, and also when we want to do post-process of the solutions. And in particular, can we solve this problem doing another formulation? Yes, I can.
X equal to 0 corresponds to the part near the surface.
Yes, the idea is that near the surface is equal to 0.
But in the previous example,
Yes. Sorry. The idea is we have
the black one.
the black one.
Yes.
Yes. Well, let me see if I can find another one marker. Because those markers are not working so well. So the idea is in this part are not working so well. Oh, this is with the fingers. It's a little bit better. So x and y. So the idea is we are doing the measurement from here to here. Obviously, following the x, only the x coordinates.
But in the previous example,
Uh-huh.
in the previous numerical example,
Uh-huh.
then
Yes. And the previous one are using just depending on y.
yes, but the error was Was the contrary, no? One
Yes.
corresponds to the farthest.
Uh-huh. Yes, because, well, in this case, when y is equal to 1, it's also here.
It's the same.
Yes, it's the same. It's the same issue. The intersection between the fault with this part. That's the problem. That intersection is doing a lot of issues in our numerical experiments. Well, we need to obtain an explanation.
Okay, so I have a question.
It's about
What is exactly your inverse problem?
the inverse problem is to recover the jump given some measurements in the displacement.
Okay, what are the measurements?
The measurements are just obtained. For example, here we're obtaining just punctual measurements from the displacement, and we reconstructed using, for example, interpolation.
Did you solve the first?
Yes, we indeed for this case we solved the direct problem, and we used the solution for the direct problem as a way to obtain the observations.
Okay, that boundary data is like
The boundary data for this case, we suppose the Dirichlet conditions are equal to 0, and the normal conditions are also equal to 0. It's just conditions that working well in this it's almost infinite domain, because it's bigger. It's bigger. For example, our selection. We have in this direction are 500 kilometers, and in the other direction are 1,100 kilometers. It's a complete bigger, it's a big domain.
Okay, so I can imagine that I'm trying to measure the result of Earth. So usually you get some information from the earthquake. Is that information related to what you're using?
Of course. Okay. The idea is to obtain information, for example, for satellite detectors, or just the different stations that the seismological agencies can put in different points, strategic points. For example, USGS, Senapred in Chile, and another institution, for example, the same University of Chile.
Is there anything behind the choice an exponential, or
it's just because some experiment we could use another curve as a reference, but the idea about using a Gaussian is because we are comparing this with another experiment that some doctoral candidate in the United States are using in the geophysical community. So we are doing some comparisons, and we could obtain better solutions in that numerical sense. And also we are trying to perform another techniques for the post-process that they can do it. That's gamma A
You
is,
also have to impose it, right?
yes, we are imposed just a point in this one. Yes. And also we can extend the faults in this sense. That would be very useful in some sense. Just impose a jump equal to 0 in this part. Yes, we can impose a fault equal to 0 in this part, and we can extend the fault from this little part to the entire.
Yeah, but I don't understand, this is what you are doing, or?
That's what we are doing in some sense, but also we are just restricting all in this blue part of.
Okay, so just imagining the picture, the left part of the line is not saying anything.
Could we say something in the new models that we are using?
Okay. For now,
For now, it's just we can just focus in this part, which is part in blue.
No, that particle is fixed.
Yes, the particle is fixed. And we recover this group with this problem in the intersection between the blue part and the black part in the on top of the surface. But we have some stability results for the inverse problem. This is just make things. I will don't show some details because I'm working in these details. So first of all, we have the classic lemma for the Hartmann waves. We have a wave that follows this kind of properties. In this particular case, we are doing some internal results. So the idea is to measure fault. The markers are not working today. Here's to measure in two different parts on the right. And we have some good results from Imanov and Yamamoto from 2003 that follows this structure. Using the weights, beta in this case is, sorry, following this structure, tau, in this case, tau. And we can obtain this kind of results. So that's the idea. The idea is to use this result in our problem using the mixed formulation. So we have here the measurements, but the problem is we have the measurements of u and the derivative of u. That could be complicated in some sense. So if we impose and define this set, this subset for so much. If we define this subset, maybe we can obtain something like that. Gamma and that. And we can obtain a recovery of gamma of S in this little range. Not in the entire gamma F, but in a very big portion. Following this inverse inequality, but theta is not equal to 1, theta is tending to 0. So it's like a whole there inequality, but it's not limited that we can expect. But it's very similar to another inequalities that we can obtain in another inverse problem. But it's not solving my problem. I have internal measurements, and right now I have measurements here, on the boundary. The idea is using some results to extend the fault here. And the idea is to extend, for example, creating a new domain. Generating a new omega-1 and omega-2. And using some trace theorems, we can obtain a result very similar to the original one. And the idea is to have these kind of problems. If we only change the gamma, S1 and S2, and all the other parameters are the same in this experiment, we can this inverse problem with this stability condition. So the idea is we need to measure two things: the displacements and the stresses, the normal stresses. But what's the point? On surface, we impose one of the two boundary conditions. In our particular case, we impose this boundary condition, so this there disappears. And we only need to measure In our case, just the displacement. In the other hand, if we impose this boundary condition, we need to measure this part. So the result is also good in the sense that it's giving us more information about what we need to measure. Depends on what is our current information. And the second one is a new variational formulation. So in this part, it's very useful to extend the fault. So the idea, right now we have, this is the original fault. What we want to extend, obtaining two domains and an interface. The interface is the fault. And we divide this domain into parts, omega-1 and omega-2. And in this case, it's convenient to use the traditional subvolume spaces H1. So in H1, we can obtain this formulation, and J is just the normal with respect to omega-1. So this is M1 and this is M2. But we need to add a new variable, the tractions on gamma F. This is our new variable. So in this case, we obtain this condition for the jumps. That would be very important. And using just integration by parts, we obtain this first element. But the tractions, the traction is this term, traction for omega-2 is negative t, not t, negative t, because we are preserving the tractions. And we're doing a very special formulation for the problem, because we can impose in a weakly way the displacement jump. So we can obtain this composition. This term is equal to 0 because S is in the tangent direction. This term is in a normal direction, so this term is equal to 0. And we obtain a new formulation, simpler than the first one. We can just treat nouns. The displacement in omega-1, the displacement in omega-2, and the fraction. It's simpler in some sense because we are not paying, we need to compute stresses, we need to compute the rotational part of U. It's simpler in some sense, but also we have a symmetric structure. So it's good for a computational sense. We can obtain the sum, the same existing uniqueness of solution using Babushka-Brezzi, but also because we're using H1, we can use Lagrange finite elements. The classical Lagrange finite elements for omega-1 and omega-2. And it's also better for post-process. One of the issues for us is to compute the traction in the original mixed formulation. We need to do a lot of code to recover T. But this new formulation is giving us T for free. So that's we have a good advantage. For example, we can compare both variational formulations. We obtain the same solutions for the displacement, but you can see the difference of degrees of freedom. In the first one, we have 236,000 degrees of freedom. In this case, 27,000. We're decreasing the degrees of freedom to the 12%. So we're doing less computational effort to obtain the same quality solution. But also we have a good advantage for the post-process. We're doing more experiments and more effort to obtain new ways to recover, new ways to solve the inverse problem, and also a new software that we are using right now. For example, all the numerical examples were performed using Phoenix 2019 with the Dolphin adjoint library. It's a library very useful to solve optimal control problems. But the issue about Phoenix is not so good when we need to work in domains with interfaces. So we need to use another library that can complement Phoenix. For example, Multi-Phoenix is a new library for that purpose. But the issue is it's not compatible with alternate units. So we need another new strategy to solve the optimal control problem. Maybe not using an solver for the optimization problem, or maybe couple the direct problem, the first order optimality condition, and the joint equation in just a very big formulation. Would be a good way to do it, but also it's very complicated for it in the coding process. Also, we have three very important things that advancing in our research. The first one is find an a posteriori error estimate. What's the idea about a posteriori error estimate? The complete result is a priori, so we need to have information about the real solution of it. In a posteriori error estimate, we don't know the solutions, and we can obtain or we can compute estimates. In the case of the unknown solutions, and using that estimates, we can design an adaptive refinement strategy. So what's the idea about the adaptive refinement? For example, we have the classic mesh. So we can compute, and we can obtain, for example, that in that triangles, we have the largest errors, because we can compute the error in every element. So we can map the elements and refine the elements in a conformance sense. Example, we can do this kind of refinement. Example here, here. We can just divide all the triangles in two parts. But we need to do some complementary refinement for the mesh in order to obtain a conformal mesh. The idea is to mark and refine as an obviously compute again the solution, mark, refine, compute again, mark, refine, doing a loop until some result optimal criteria is reached. And of course, we need to analyze process technique and semi-discrete schemes. The idea about the optimization technique is we have the problem, we have the continuous problem and the discretized problem. We discretize and optimize. But in some sense, we can to optimize and after that discretize the problem in the optimal control set. That could have different solutions, but we are using the same convergence order. But the idea is trying to have a way to perform this kind of semi-discrete schemes, where the order between the discretization and optimization could be changing. And maybe we could have some better solutions for that points where the numerical solution is not working well. Obviously, another future work is to improve the theoretical results for the inverse estimate. I have some good ideas that I talked to with Axel 2 months ago, but I detected some mistakes in my computations, in my notes. So the idea is to polish to improve that proof and trying to set a proof to a journal and something like that. We have a preprint for the numerical results that is doing It's a very good advanced stage in a journal, so I'm positive things. If you have another questions, you can see the preparing in my research case profile and the classical papers for that. This is the principal paper of the idea about the problem. This is Simon Puel and all the professors that have collaborated with Puel. This is Ronald Wexler is one of the best papers for all the people that want to work about applications of finite elements in optimal control. Imanol Yamamoto, the paper for the Kalman inequalities, and this is a classical paper for all the reference about the mixed finite element formulations like the first one. So that's my presentation. Thank you for your attention.
For the presentation, the interactive presentation.
Yes, the one words markers are excellent. It's very colorful.
And does anyone have any question or comments?
Yes, just one question. Since it during the presentation, show again another variational formulation simpler.
Yes, a simpler variational formulation. Yeah.
And why you are not using simpler formulations to try to update the problem?
Because we are thinking in this new formulation from 2 weeks ago.
Okay. Do you think it's simpler to see the stability of the problem for this?
Yeah. I'm doing a new calculation for this problem is a simple way to obtain the inverse inequality. In this case, it's simpler.
And in some sense, this new formulation gives less interest to the first paper. In the sense
For the first paper, the idea in this new formulation that we have an advantage. For the optimal control problem, we don't have the need to project to H1. So we simplify that. This is very important for the perspective about the joint problem. Some terms will disappear, are more simpler in general, and also we have the advantage. We have also first of that advantage, but we have the disadvantage that because we need to use multifinix, we can perform some experiments using dominant joint.
okay,
So we need to rewrite some things to maybe doing a new scheme to solve the optimal control problem. But this, and also we will have the theoretical result for the convergence. But this performs very well. If we have some numerical results, this result well. But we need to obtain all the a priori estimates for the problem.
How do you protect from L2 to H1?
Why?
No, how?
How? In computational sense?
Yeah, or in theoretical.
In the theoretical sense, you have to solve this case. So P1 U minus U. So the idea is to perform this in the sense we need to solve this problem. Py U B sub omega equal U B sub omega for all B in H1. We need to solve this variational formulation. The projection from L2 to H1. In the L2 sense. We're testing with all the H1 elements.
H1 is dense.
H1 is dense to L2. Yeah, that's true. we are testing just in H1.
Okay. Yeah, I
Mhm.
see it. And then the other thing, corner, where the fault hits the boundary, that when you have a corner
Yeah.
in the domain, that's creating a
Yeah,
problem.
well, that kind of corners.
Yes,
Yeah. Right now is well, we are trying to do in an explanation in a computational sense. The classical answer for the numerical community is just refining that part. It's a theoretical sense. We don't know the answer. It's complicated for us to have the answer. Yeah, it could be something because we are suppose some smoothness of the solution for the theoretical and numerical results. We wish to have good properties in the smoothness. Maybe, in some sense, we could have something like that, very smooth. But we don't have that smooth. So some discontinuity in that part could be very tricky for
that's theorem.
for test theorems. So that's why we have these issues in this test. So that's why we need to project. And maybe the projection is adding some noise in that part in our observations. That's why we prefer to do it a new variational formulation that is separated the space in two different H1 spaces. So we don't have issues to compute traces because we have traces. But it's different on the left-hand side and the right-hand side of the fault.
Any question? Any question? Let's say thanks again.